RL transients, the storage phase. The equation for the transient response of the current through an inductor is the following. IL equals E by R 1 minus e to the power minus t by tau amperes, with the time constant now defined by tau equals L by R. The equation for the voltage across the coil is the following. VL equals E times e to the power minus t by tau. And the voltage across the resistor VR equals E times 1 minus e to the power minus t by tau. So, the graph for the current through the inductor will look like this, and the voltage across the inductor will form a graph of this type. The voltage across the resistor will vary in this manner. Since the waveforms are similar to those obtained for capacitive networks, we will assume that the storage phase has passed and steady state conditions have been established once a period of time equal to 5 time constants has occurred. The current cannot change instantaneously in an inductive network. The inductor takes the characteristics of an open circuit at the instant the switch is closed, and the inductor takes the characteristic of a short circuit when steady state conditions have been established. Example 2. Find the mathematical expression for the transient behavior of IL and VL for the circuit as shown over here. If the switch is closed at t equals to 0 seconds, sketch the resulting curves. Now, at first we need to determine the time constant tau, which for this network will be L by R1 equals 2 milliseconds. Then, in order to derive the expression for IL, we need to determine the maximum current flowing through this network. The maximum current will flow through this network when the inductor will reach the steady state. That is, the inductor can be replaced by the short circuit equivalent. Hence, the current flowing through the network at that point of time, that is during the steady state condition, will be equal to Im, which is equals to E by R1, 25 milliampere. Substituting this value in the expression for IL, we can determine that IL equals 25 milliampere 1 minus e to the power minus t by 2 milliseconds. Then we need to determine the expression for VL as well. VL will be equals to 50 volts e to the power minus t by 2 milliseconds. And this is how the graph of IL and VL will look like. Initial condition. Using the transient equation developed in the previous section, an equation for the current IL can be written for the entire time interval in figure 11.38. I is the initial condition current, the final condition current is IF, and the transition between the two current levels is IF minus II. Substituting these in the expression of IL, we get IL equals II plus IF minus II times 1 minus e to the power minus t by tau. On rearranging the terms, we get IL, considering the initial condition, to be equal to IF plus II minus IF e to the power minus t by tau. Example 3. The inductor in figure 11.39 has an initial current level of 4 milliampere in the direction shown. So we need to find the mathematical expression for the current through the coil once the switch is closed. Then we have to find the mathematical expression for the voltage across the coil during the transient period. And then we have to sketch the waveform. Now, we know that the maximum current through the circuit will be when the inductor reaches steady state condition. Hence, IF will be equal to E by R1 plus R2, which is 1.78 milliampere. Tau will be equal to L by RT, which is going to be 11.11 microsecond. In substituting these values in the expression for IL, we'll get IL equals 1.78 milliampere plus 2.22 milliampere e to the power minus t by 11.11 microseconds. Since the current through the inductor is constant at 4 milliampere prior to the closing of the switch, the voltage, whose level is sensitive only to changes in the current through the coil, must have an initial voltage of 0 volt. At the instant the switch is closed, the current through the coil cannot change instantaneously. So the current through the resistive elements will be 4 milliampere. The resulting peak voltage at t equals to 0 second can then be found using Kirchhoff's voltage law as follows, which will be equal to minus 20 volt. Note, the minus sign is used to indicate the polarity of the voltage VL is opposite to the defined polarity. The voltage then decays with the same time constant as the current to 0 because the inductor is approaching its short circuit equivalence. Hence, the equation for VL is therefore VL equals minus 20 volt e to the power minus t by 11.11 microseconds. The waveform for IL and VL will be as shown over here. The initial and final values of the current were drawn first, and then the transient response was included between those levels. That is, the initial level was drawn over here and the final level was marked over here. Then these 2 points were connected. For the voltage, the waveform begins and ends at 0, with the peak value having a sign sensitivity to the defined polarity of VL. Hence, initially it will be 0 volts, then minus 20 volts the moment the switch is closed, and after that it will decay and become 0 again. RL transients, the release phase. In the analysis of RC circuits, we found that the capacitor could hold its charge and store energy in the form of an electric field for a period of time determined by the leakage factors. In RL circuits, the energy is stored in the form of a magnetic field established by the current through the coil. Unlike the capacitor, however, an isolated inductor cannot continue to store energy because the absence of a closed path causes the current to drop to 0, releasing the energy stored in the form of a magnetic field. If the series RL circuits as shown over here reaches steady state condition and the switch is quickly opened, a spark will occur across the contacts due to the rapid change in current from a maximum of E by R to 0 amperes. The change in current of di by dt of the equation VL equals L times di by dt establishes a high voltage VL across the coil that in conjunction with the applied voltage E appears across the points of the switch. If opening the switch to move it to another position causes such a rapid discharge in stored energy, how can the decay phase of an RL circuit be analyzed in the same manner as for the RC circuit? The solution is to use a network like that shown in figure 11.42a. When the switch is closed, the voltage across resistor R2 is E volts, and the RL branch responds in the same manner as described above with the same waveforms and levels. Why? Because R2 is connected in parallel with E. Hence, the voltage across this branch will remain the same as it was before. A Thevenin network of E in parallel with R2 results in the source as shown in figure 11.42b. Since R2 will be shorted out by the short circuit replacement of the voltage source E when the Thevenin resistance is determined. After the storage phase has passed and steady state conditions are established, The switch can be opened without the sparking effect or rapid discharge due to resistor R2, which provides a complete path for the current IL. The voltage VL across the inductor will reverse polarity and will have a magnitude determined by VL equals minus VR1 plus VR2. Recall that the voltage across an inductor can change instantaneously, but the current cannot. The result is that the current IL must maintain the same direction and magnitude as shown. Therefore, the instant after the switch is open, IL is still Im equals E by R1. VL equals minus VR1 plus VR2. Substituting these values, we'll get VL equals to minus R1 by R1 plus R2 by R1 times E. Thus, VL can be expressed as minus 1 plus R2 by R1 times E when the switch is open. This shows that VL is bigger than E volts by the ratio R2 by R1. In other words, when the switch is opened, the voltage across the inductor reverses polarity and drops instantaneously from E to minus 1 plus R2 by R1 times E volts. Thus, as an inductor releases its stored energy, the voltage across the coil decays to zero in the following manner. VL equals minus VI times e to the power minus t by tau. VI equals 1 plus R2 by R1 times E. Tau prime will be equals L by RT. The current decays from a maximum of Im E by R1 to 0 using equation I equals E by R1 and IF equals 0, we can determine the final IL, which is equals to E by R1 e to the power minus t by tau prime, and tau prime will be equal to L by R1 plus R2. These equations will be easier for you to understand once you solve a problem. The mathematical expression for the voltage across either resistor can then be determined using Ohm's law, which is VR1 equals IR1 R1 and IL R1 or E by R1 times R1 e to the power minus t by tau prime. Hence VR1 equals to E times e to the power minus t by tau prime, and VR2 will be equals to minus R2 by R1 E times e to the power minus t by tau prime.